Lucky has come with his dad to see their new house. The house is almost finished, only the lighting work is left, and just then the contractor arrived.
These are some bulbs. Pick whichever one you like and I'll have it installed. These 5 bulbs range from 10 to 30 watts, but this one here is the best. We supply this one ourselves. It's just a bit more expensive. And tell me which one would be right, since more watts mean a higher electricity bill, but it will also give more light. Let's go with one of the mid-range ones.
Alright then, get mine installed. It's a 20-watt bulb. When Lucky looked at the bulb, there was no power rating written on it.
All the others have power ratings. Why doesn't this one? I skipped printing the rating to save on costs. Trust me, it's 20 watts.
But Lucky still wasn't convinced, and he wondered if there might actually be a simple, practical method to accurately determine this bulb's precise power rating. That's when he noticed the ratings on the other bulbs. 2 combinations formed a common ratio. It reminded him of Mr. Rajvan's physics class.
Today we will learn about the wheatstone bridge. It's a technique where using known resistors we can determine the value of an unknown resistor. In a wheatstone bridge, 4 resistors are arranged in parallel like this, and across the bridge there is another resistor, such as a bulb. Bulb will go out only when the wheatstone bridge is balanced, meaning the ratios of these resistors are equal to each other. But sir, how does that happen? Because the bulb going out means that the voltages at these 2 points are equal. If we call the current in the left branch I and in the right branch I, then the voltage drop across resistor R1 is equal to the current I multiplied by resistance R1, and similarly across resistor R3 it is I times R3. For equal bridge point voltages, resistor voltage drops must be equal.
We get the ratio I equals R1 to R3. Applying the same logic to R2 and R4. There too, the ratio of I to I equals R2 divided by R4. That is R1 or R3 equals R2 R4.
Meaning if the bulb doesn't light and we know the values of 3 of the 4 resistors, we can easily calculate the unknown one. Lucky used this concept.
On bulbs, he arranged 4 identical bulbs, each having the same power rating in this precise layout, and then gently placed a 5th bulb at the center of the bridge to test whether any current would flow through it.
But the wheatstone bridge works for resistors. Will it work for power too?
It will, because power is V squared over R. From this, R equals V squared over P. A bulb's power is specified based on the mains voltage in our homes. And note that RPK is inversely proportional, meaning that if the power of one bulb is twice that of another, then its resistance will be half, which in a balanced bridge means it will be the exact opposite of the original configuration. And note that this ratio still remains consistent for all 4 bulbs, regardless of their precise placement in the electrical circuit.
That is, if this bulb is 20 watts, it will form a balanced wheatstone bridge and no current will flow through the middle wire when Lucky switched on the circuit.
But what's this? The middle bulb actually lit up, which means it's not 20 watts.
Wow, you're so smart. Uncle, don't mess with the physics kids from the lax batch.